So today we're going to be creating a really simple ray tracer. This lecture probably feels like it's a little bit out of left field. It's a little bit more advanced. We've been building up rasterization, and now suddenly we're completely switching techniques. But ray tracing is a very simple way to introduce a lot of advanced graphics concepts in a way that doesn't explode people's brains. Trying to wrap your head around the rendering equation in a rasterizer is painful when it's 5 lines of code in a ray tracer. Before we get started, we need a couple of utilities to help us here. So, first order of business, we need some way of rendering out a file. In the description of this YouTube video, there should be a link to the PPM image writer that we wrote for the rasterization video. So I'm going to give that a quick grab. So we'll throw that in ppm.hpp. And then second order of business, we need some sort of utility for giving us math libraries. We could write all of our math ourselves, but we're just going to use a library to do a lot of our vector math, our positions, that kind of stuff for us. So when I add a git submodule, which we're going to do real fast, github.com/docsci/studmath, it adds a new folder that is that repository, but it also adds this git modules file. And if we check the git status, which is how we see what needs to be committed, what's staged, all that kind of stuff, we'll see that we have the git modules and the studmath folder staged. So normally you can't stage a folder, you can just stage a file inside of it. But with a submodule, the entire repository gets added as this one reference and a commit SHA. So what did we just add as a submodule? Well, it's the math library that I've been working on for the game framework. So if we take a look in here, we'll notice that there's a file called vector.hpp, which gives us vectors that are templated on types and sizes, so we can make like float 4s. And they have a lot of operators specified on them. So they implement stuff like multiply, divide, modulus, addition, subtraction, all the stuff you would actually probably want. And they do it using the new C++ SIMD acceleration. So they do it very fast. So we're going to be using this for our math. So we have code to write out an image, and we have some math code. To get started, we're going to make our hello world example that we always start our environments with. So we're going to make a file called raytrace, just trace.cpp. And then we're going to quickly type out our int main hashtag include IOStream. I can type today, stud cout hello world, stud endline, and of course our CMake lists. CMake lists.text, use latest GCC, CMake minimum required version 3.21, and we're going to add our executable trace.cpp, and when we give that our regular build, we get hello world, but we want to tweak a few things now. If you look at this math library, there's a CMake list that sets it up as a library for us. So what we can do to import all of that CMake code for us is just add subdirectory studmath. So the path to whatever folder we want to add. Now, all of the library stuff that the math library has is available to us. So we can go target, link libraries, trace, and give it a public library. And what did studmath give us? It gave us stud : math. So at CMake line, it's not happy about that. So now when we give this a build, all of the studmath utilities should be available to us. Cool. So what exactly does that mean? That means that I can include math/namespace alias.hpp. And now I should have access to stud math vector float 3 math vec. And so this is a 3-dimensional vector. And if we give that a compile, and of course, we need to target set target properties, trace properties, CXX standard 26. We have access to this vector 3, and we're going to use it for a couple of things. So we're going to make a couple of defines for it. Then we're going to go using vec3 is studmath vector float 3. So that'll be like directions. Then we're going to go using point 3 equals studmath. It's not going to actually be any different. We're just going to use point 3s to indicate that we're talking about a point in 3D space instead of something else. And then one last one. We're going to go using color F is equal to our vec3. So I named it color F because when we include our ppm.hpp file, you'll notice that it specifies its own color with an RGB. So we're going to use color F to do float colors, and then we're going to convert them to the ppm colors. So we're going to quickly insert a conversion function. So color convert color F, C, and we're just going to return C.x, C.r times 255, C.green.255, C.blue times 255, and it's complaining that it cannot be narrowed, so we'll insert the explicit casts that it wants. So what we're doing here is we're going to have a float color where our values are going to range from 0, meaning black, to 1, meaning full. So 1 is full red, 1 is full green. And then we want to convert that to the 0 to 255 color system that a ppm image wants. So just a really fast function to do that for us. Now we would like to set up a pixel grid. So I'm going to make a little struct here, which I'm going to call pixel grid. And we're going to template it on a width and a height. And we're going to make this a stud array of our ppm colors and X and Y. And I believe C++20 is going to want that to say public. So what this does is it just represents the array of colors that we had in the last rasterization. So it's our image that we're actually going to do, but we're going to add a little helper function this time to make the printing easier. So we're going to add something that gives us a stud span of colors, not colors, color, and we're going to call this linear. And then this will just return the linearization code that we wrote last time. So this data, X times Y, or how big it is. And that allows us to very quickly convert our 2D array of colors into a linear array of colors that we can print out easier. There's another utility that we're going to add just to set the color of the image. So I'm going to go image reference, since I like to return it so I can chain them. Fill, color C, and we're going to just set it to black by default. Image, pixel grid, auto view equals linear. So we'll make the linearization, and we're just going to fill the linearization with that color. And then for chaining purposes, we return this. If we were to write like a void function and not return anything, that would work just as well. But I tend to avoid writing void functions and instead return the type itself. And that way you can write code like image.fill, which becomes useful when you're not calling the same function twice. Something like generate mipmaps dot upload to GPU is a little bit nicer to write than having it on two separate lines, in my opinion. So I tend to avoid using void and instead we just return a reference to the thing itself. We can start talking about some math. If we're making a ray tracer, the most important concept to understand is array. So not to be confused with the C array, so like a bunch of values, we're going to talk about the mathematical array. So what is array? In its simplest form, you can think of array as a line with an arrow. But an arrow has two important parts to it, right? It has the point where it begins, and it has the direction that it's going and how far it's going. So we have what's called an origin, and we have what's called a magnitude or a direction. Both of these things are important here. We care about the direction and we care about how far we're going to go. We can make a little parameter called t, and we can slide t along this line. So down here at the origin, we're going to have t equals 0. And up here at the point, we're going to have t equals 1. So just this parameter that we're going to allow to slide across the line. But we're going to do a little bit more interesting. We're going to allow t to go bigger. So like out here might be t, my green, t equals 1.2 or something. So we're going to allow, no, not a vector, because vectors only have the magnitude, right? A ray has this origin. So you can think of a ray as a vector at a point in space, if that makes sense. Because we always think about vectors as being positioned at the origin of space, even if we're thinking about adding them and doing weird things. So we like visually slide them around space. A vector always starts at 0, 0. A ray can start somewhere else, and that makes them a little bit more powerful. Powerful enough to have it start, say, at a camera, and then we have a direction that moves from the camera into the scene. Does that make sense? So we have our ray. We have our idea of a t parameter that we can slide back and forth. So let's go implement that. For starters, we're going to want a little struct to represent our ray. So a ray will have a 0.3 for that origin, and it will have a vec3 for that direction. And then one more little bit of helper. I'm going to override the square brackets, which will give us a 0.3. So operator, square brackets, and it'll take t. So we can convert a t to a point along the ray. And to calculate that, it's very simple. It's just returning the origin plus the direction times t. The joys of having a math library to help us. So we can now find any point along this ray or further than the ray based on this t parameter. We now need to set up a couple of things to start drawing out an image. So the first is we're going to have a size t for the width of what we want to render. We're going to go with 400. Ray tracing is expensive. You're going to see by the time we're done here, it's going to be taking like close to a minute to be rendering out these little 400 pixel images, because we're going to be doing this super inefficiently, the CPU, and this is like the perfect task for a GPU. To calculate the height, we're going to add another variable, const expr float aspect is going to be 16.0 over 9. And we're just going to calculate our height by multiplying width by our aspect ratio. By the way, this aspect ratio is the normal aspect ratio for most monitors. A 1920 by 1080p monitor is going to have a 16 by 9 aspect ratio. We're also then going to create a pixel grid with that width and height, and we're going to call that our image. And we're just going to fill that image with black. So now, let's write the code to quickly write out that image, which, since we wrote a couple helpers, is really simple. We have that write ppm function that we did last time. We know the width and height of the image now, and we can go image.linear to get the color data. So last bit of information we need is a std of stream fout, and we're going to call this result.ppm. So if we write the image to fout, we should get, when we run this, we should get nothing. There we go. An empty ppm image. And the numbers are backwards. So we're going to do width divided by the aspect ratio instead of width times the aspect ratio. And now we have a screen proportioned image. It's empty, black, not particularly interesting. So let's fix that problem. So to make things a little bit more interesting, we're going to trace some rays. So we have a camera, and the camera's job is to take in pictures of light. So all of the light that's coming off the sun is coming into the lens of the camera, and the camera then puts that through some process that's too complicated and beyond the scope of this explanation. But some sort of black magic happens, and we get an image. It gets either put onto film or put into digital space, and we're happy. Well, it turns out that doing it this way, where the light comes to the camera, is way too expensive for a computer to compute. It ends up taking forever to like get enough light built up to actually see anything. So it takes like days to render stuff this way. So instead of doing that, our approximation is that we're going to do the opposite. We're going to shoot rays from the camera, and we're going to see what they hit. So our goal now is, how are we going to set up these rays? Well, what we're going to do is we're going to create a plane in front of our camera. This is called our image plane. And we're going to calculate the point from here to here. And if we now draw this from like the front, so our camera is here, right? We're calculating the ray that goes from the camera to this point, from the camera to this point. We want this to be a pixel grid, right? So then we take the ray to the next point in the pixel grid. Does that make sense? So right now, the way I've drawn it, I'm kind of suggesting that we're going to measure at the top of the pixel, but it's a little bit better, per se, to try and measure what the ray looks like in the middle of the pixel. So we're actually going to be trying to trace the ray to the middle of the pixel. And remember that we said that our t parameter can extend beyond our ray. So even though our ray ends at this image plane, we're going to be able to draw things that are beyond the image plane. So let's implement this creating rays across our image. So for that, we're going to need a couple of things. First off is we're going to need a const expr float plane depth, which you're going to set to 1. If you're a photographer, they call this focal length. So it's the distance away from the camera that the camera is focusing. And now we're going to set up how big our viewport is. So back in this image, this plane that we're shooting our rays through is called our viewport. It's the window into space that we see through. So we're going to define in world space, not screen space, how big that viewport is. So we're going to set const expr float viewport height, and that's going to be 2. And then we're going to calculate the viewport width as the viewport height times our aspect ratio. Notice that when we're calculating the height from the width, we need to divide. When we're calculating the width from the height, we need to multiply. Oh, sorry, not the aspect, as a float conversion of the width over the height. Because we're going to lose some precision here, and it might not be exactly 16 by 9. So we want to use the actual aspect ratio that our width and height give us instead of the perfect 16 by 9. It's probably going to be like 16 by 9.5 or something. It's because of pixel rounding error. Auto camera center, which is going to be a 0.3, and it's just 0, 0, 0. We'll make that explicit. 0, 0, 0. So our camera is positioned at the origin of the world. So now our goal is to calculate this variable called top left location. So it's exactly this ray here, right? We want to calculate the point of this top left relative to our camera, and then we can create a ray that goes to it. So we need a few bits of information for this. We need our camera center, and then we're going to subtract off a vector 3 for our focal length, our plane depth. We're picking z, and what we're saying here is that the camera is going to be looking forward into the z direction. And now that we have the point of the plane, so we have, let's draw this, we have this point. We need to do the offsetting. So we need to figure out how far up and to the left we need to go. So what I'm going to do is I'm going to split off vec3 viewport x is going to be the viewport width, so along the x direction, and vec3 viewport y, which is going to be 0, the viewport height, and 0. And there's this little property that space tends to go down. We want the top left corner of our image to be at 0, 0, and we want space to go down in image space. So to represent that in 3D space, we need our viewport y to be negated. And now what we can do is we can subtract off the viewport x, which we multiply by 0.5, and we can subtract off the viewport y, which we multiply by 0.5. So viewport x represents the whole width, but we don't want the whole width, right? Because we're at the center. So we don't want to go from the center the whole width. We want to go from the center half the width. We don't want to go from the center the whole height. We want to go from the center half the height. So we've now calculated the position of the top left corner. But we just said that we didn't want the top left corner. We want the middle of that pixel. So we need to figure out how big a pixel is. So we're going to go vec3 pixel width is going to be the viewport x divided by the width, and vec3 pixel height is going to be the viewport y divided by the height. So in world space, we now know how big a pixel is. And so the last thing we're going to do is we're going to add our pixel width times our pixel height, times plus, and that again multiplied by 0.5. So we calculate the center of the viewport, we calculate the top left corner, and then we move half a pixel in. And that's why the 0.5 is here. We don't want to move an entire pixel in. We don't want to move to here. We want to move half a pixel in, so we're at the center of the pixel. Sound good? So we are officially at the point where nothing has happened. Isn't that phenomenal? But we can start doing something. So we're going to create what I'm going to call the main render loop. So we're going to go for size underscore t, y equals 0, y is less than our height, plus y. And then for size underscore t, x equals 0, x is less than width, plus x. And what we're going to do here is we're going to go image y x, and we're going to set it equal to convert. And we're just going to do like a teal type image. So half green, half blue. And when we run this, we now have the world's ugliest teal. Would you believe me if I said that we were now ready to start doing ray tracing? We technically have a ray tracer already. Kind of. We're one step away from having a functional ray tracer. To make a ray, we need 2 bits of information. We need the origin, and we need that direction, right? So the origin is very simple. It starts at the camera center. The direction is a little bit harder. We need a location of this pixel, so pixel location, and then the direction is the pixel location minus the camera center, the vector from the camera to the pixel location. So what is the location of the pixel? Well, it turns out that it is the top left location plus our x times how wide a pixel is, so pixel width, plus our y times how high a pixel is. And that will give us the location of the pixel in world space. And then we want to make a ray r from this. And the ray takes 2 things. Its origin is equal to the camera center, and its direction is equal to the pixel location minus the camera center. We have a ring. Okay, so let's now do something with the ray. So we're going to create a new function here, which you're going to call color f ray color. This is going to take in just a ray, so a const ray reference ray. And right now, we're just going to move returning our ugly teal into this ray color. And now we're going to go ray color as our ray. We give it a run, and we now technically have a ray tracer. We have sent a bunch of rays into a scene. They found that the color they hit is teal, and they told us that. We have successfully implemented a ray tracer. It's not particularly interesting, but it is a ray tracer. So let's start making this ray color function. So what color does the ray hit? A little bit more interesting. So we're going to start by defining a nicer background color. We're going to do an interpolation from kind of a white at the bottom up to kind of a blue at the top. We're going to go white to blue. So to do that, we need a little bit of information. We want to know what direction our ray is facing. So vec3 u, so normalized, is the normalization of our ray. Sorry, not of our ray, of our ray direction. If you recall, normalization means make the length 1. And so now we're going to have an interesting situation here. If we take the normalized .y, this should be between approximately -1 and 1. So when we're hitting the bottom of our viewport, it should be getting close to -1. The normalization is going to mean it's a little bit short of -1, but we're gonna say it's -1 for easy math. And when we're hitting the top of our viewport, we should be close to 1. So what we're going to do is we're going to remap this from -1 to 1 to 0 to 1. We can do that by multiplying by 0.5 and then adding 1. So the multiply by 0.5 gets us into the range negative 0.5 to positive 0.5. And then when we add 0.5, we go from negative 0.5 to 0 and positive 0.5 to 1. And so this is going to be a t parameter that we're going to use for a linear interpolation between two colors. And the ones I have here are a white at the bottom. What did I pick for white? Just one across the board. So color F1, which we're going to broadcast. And we're going to do this when the t is 0. And a color F 0.5, 0.7, 1, which you're going to do when it's 1. So we're going to multiply our one color by t, and then we're going to add that by 1 minus t times our 0 color. So when t is 1, we're going to be blending in 100% of this color. And when t is 0, we're going to be blending in 100% of this color. And as t changes, this is the proper formula for nicely interpolating. And if we now run this beautiful tracer, instead of getting our super ugly teal, we should now have this really nice blending between a white and a blue. So we now have a ray tracer that can just give us a linear background color. But if I were to show you this and tell you that it was ray traced, you'd be like, yeah, sure, that's not interesting. So let's add in an object to make it a little bit more interesting. And to talk about an object, adding an object, we're going to have to talk about some more math. So our goal here is that we want to take this image and we want to add like a sphere in the middle of it. That is our goal. So how do we do that? Well, we have our object, our sphere that we want to hit, and our goal is we have our origin and we have our ray that hits our plane, and we want to find where, if we continue this ray out, it would intersect. So given our ray R, we want to find the T where R intersects the sphere. Okay? That is our goal. So what is the math here? It's going to start off a little bit weird, and we're going to build up. So remember, our goal is to find T of intersection. So that weird point along the ray where we actually intersect. First off, let's start with the equation for a sphere. So a sphere is defined by x squared plus y squared plus z squared equals r squared. So its points, the point in 3D space of its surface is equal to its radius squared. So the surface of a sphere solves that equation. So we don't necessarily want a sphere at the origin though. So we're going to instead do the sphere c dot x, so center dot x, minus x, all of that squared, plus the center dot y minus y squared, plus c dot z minus z squared equals r squared. Cool. So this is where c is center of sphere. We're not going to rewrite this in terms of c's and p's, where p is points in consideration. So the point we want to care about. So we have c dot x minus p dot x squared plus c dot y minus p dot y squared plus c dot z minus p dot z squared equals r squared. So observation here. Isn't c dot x minus p dot x, right? So if we make that a thing, so like u equals c minus p, isn't this u squared plus dot x plus u dot y squared plus u dot z squared equals r? And isn't this just the dot product of u with itself? So that means that we can rewrite this formula as the dot product of c minus p with c minus p, and that's equal to r squared. If this is true, this tells us that the point P is on the surface of our sphere. So what can we do with that? Well, if instead of having a point P here, we replace P, so dot C minus ray dot at T, C minus ray dot at T, suddenly we now have an equation in terms of T that we can solve to find out if a ray has some T that is on the surface of the sphere. So we're going to rewrite this a little bit. We're going to pull out the ray dot at. We're going to start from this dot product we just found. So dot of the center minus the origin of the ray plus t times the direction of the ray, dotted with c minus the origin of the ray plus t times the direction of the ray is equal to r squared. So we're starting there. And now we're going to do a bunch of really gross algebra to distribute this multiplication across the dot product. And I'm not going to work all of that, so I'm going to ask everyone to trust me that we can now go to this is equal to t squared times the dot product of the direction with itself minus 2 times t times the dot product of the c minus o, so the center of the sphere minus the origin of the ray, plus the dot product of the center of the sphere minus the origin dotted with itself. And all of that is equal to r squared. And now that we are here, we can do one more little algebra trick. So we're going to tweak the end of this formula a tiny bit, and we're just going to say that we move the r across, so minus r squared is equal to 0. And anywhere that this formula is true, we know that our ray intersects with our sphere. So where is this true? Well, it turns out that what we have here looks an awful lot like a times t squared plus b times t plus c times nothing, right, equals 0. Isn't that a quadratic where a is equal to t squared times the dot product of d with itself, b is equal to -2 times the dot product of d with c minus o, and c is equal to the dot product of c minus o minus r squared. And then, as a reminder, can't we just use the quadratic formula? So negative b plus or minus the square root of b squared minus 4ac over 2a to solve quadratics. And hey, look, we just identified what a, b, and c all are, so we just need to make it. Congratulations. We now have the math to solve the analytical solution to whether a ray intersects with a sphere. It is all on the screen right now. So there is an interesting note here, though. Our formula has a plus or minus in it. That means that there can be two formulas, right? It also has a square root that can be negative, which means that there can be 0. So what does it look like when there are 0 solutions? Well, that means that we have our sphere and our ray misses our sphere. What does it look like when we have one solution? We have our sphere and our ray just barely grazes the sphere at this one point. And then if we have 2 solutions, we have our sphere and our ray hits our sphere twice. So how do we implement this? Up here in our ray color, we're going to start by, actually, we're not going to do it in here. We're going to make a new function. So we'll hit sphere. So we want a couple of things. We want a 0.3 for the center. We want a radius. We want our ray. And now we're going to do math. So we're going to go auto A equals dot of ray dot direction with ray dot direction. A equals the dot of ray dot direction with ray dot direction. Auto B equals -2.0 times the dot of r dot direction, center minus r dot direction. Note here that the t's, actually there shouldn't be a t in there. That was a mistake on my part. Because remember that a is what we're multiplying by t squared. And then auto c is equal to the dot product of center minus ray dot origin, center minus ray dot origin, minus radius squared. Cool. And now we're going to do a little optimization here. It turns out that taking square roots on a computer is very expensive because it involves a loop. So we want to avoid using square roots whenever we can. But it turns out that we can do a quick little check to see if they miss or not, right? Because if the stuff inside the square root is negative, that means that we're going to get an imaginary solution that falls into the case where our ray misses the sphere. So if the stuff inside the square root is negative, we miss. So let's calculate that. So auto inside square roots, is b times b, so b squared, minus 4 times a times c. And if inside square root is less than 0, we return false, and otherwise we return true. This is an ideal code, but we're going to very quickly make it a little bit more complicated. But this is enough so that we can go if hit sphere at 0, 0, negative 1 with a radius of 0.5, and we hit it with our ray. Then instead of returning our beautiful background color, we're just going to return red. So 1, 0, 0. And if we give that a quick little run, I got it backwards. I was supposed to say ray origin, not ray direction. Oops. But just printing a red sphere isn't particularly interesting. We're still at the point where if you show someone this and you're like, this is ray trace, they're like, yeah, right, that looks horrible. We're going to calculate the normals of the sphere, and then we're going to figure out how to get rid of all this ugly aliasing, and we'll talk about exactly what aliasing is, and we'll figure out how to do some simple coloring after that, and we'll talk about the rendering equation. So to calculate normals, what we're going to do is instead of just returning true here, we're going to return a stood optional, which includes some information about the hit. So what information is useful to know about the hit? Well, one easy piece of information that we have is our t. So our goal here is to calculate the t where we hit, right? That's what we're solving. It might also be useful to have a 0.3 where we actually hit, right? So the position of the hit. And I also just said that I want the normal. We want our position at the center going out and then normalized, and that should tell us the normal. So if we miss, there is no hit information to return. And then if we don't hit, then we can do our square root. So auto square root is stood square root of the stuff inside the square root. And then let's solve the rest of the stuff. So auto root equals negative b minus the stuff inside the square root over 2 times a. And then we're going to do a little readme here, right? What if other root is needed? So we're going to stick a pin in that idea, and we'll come back to it later. But we're going to make our hit info out, and out.t is going to be equal to our root. Out.position is going to be equal to our ray at out.t, and then out.normal is going to be equal to out.position minus center, since we just mentioned that the normal is in the direction of the center going outward, but we want to normalize it. So we can either normalize it, or we can observe the fact that the radius, right, is exactly the same length as this. And so if we just divide by the radius, we'll get a normalized version. So radius, and this is equivalent to normalize out.pos minus center. Just a little bit cheaper. And then instead of returning true, we return out. And if we just compile this, I believe nothing should change. We're not using any of this extra information. Cool. So let's use it. So auto hit equals hit sphere. And we're going to check if we hit. And if we hit, we're going to return hit normal instead of our color. And fingers crossed, the live demo doesn't explode. Oh, hey, look, live demo exploded. No, this is fine. That is correct. We're getting normals from -1 to 1, and we need colors from 0 to 1. So we're going to quickly remap the normals from -1 to 1 to 0 to 1. And hey, look, it's almost like we have code to do that. So we multiply it by 0.5, and then we add 0.5, cast to a vector. And we now have a beautiful sphere. So what are we going to do about all these jagged edges? These are what we call aliasing, where there's a very sharp transition in the pixels between one object and another. It creates these really ugly jaggies, these aliases. So how do we get rid of that? Well, if we're doing rasterization, it's a really scary process. If we're doing ray tracing, we can just sample a bunch of times. So what we're doing here is for every pixel, we're taking one sample. So instead of taking one sample, what happens if we take a bunch at like a bunch of different points and average them all together? So what we were doing is we were taking like a point in the center of the pixel. What happens if we take a bunch of random points in the pixel and then average all of those values together? So we're going to need a little bit of setup for this. So first order of business, I need a function to give me a random number. So we're going to go float random in range, float min set to 0, float max we're going to set to 1, and we're going to drop in some really scary C++ standard library code that generates a random number for us. We're setting up a random distribution from our min to our max, and then we're picking one of their random number generators, and we're generating a random number that changes every time. This code is scary. Don't ask too many questions, and we'll be fine. All you need to know is that every time we call this function, we're going to get a different number between these two values. Now, we're going to want a new constant up here at the top of our main. So we're going to go const expr size t samples pixel, and this is going to be equal to 10 for now. And now we need to accumulate a bunch of samples. So right now we have one sample. So we want to go for size underscore t s equals 0. S is less than samples per pixel plus s. And we're going to make a new color that we can average these all together in. So color f temp, and we're going to move this code down here, and we're going to add the ray color onto temp, and now we're going to temp divided by samples per pixel, and we want to set temp equal to 0, and we want to plus equal temp. Is pre-incrementing really an optimization? Yes. If you look at the way post-increment tends to be implemented, the post-increment operator is something along the lines of auto temp equals star this plus star plus this return temp. So we have this extra copy that happens on the post increment, whereas if we just use the pre-increment, we skip that extra copy. So if you don't need the value before you incremented, it's usually better to use the pre-increment than the post-increment. Default to pre-incrementing unless you have a reason to post-increment. If we now render this out, first off, you notice it takes a little bit longer, and I broke everything. That's probably because I need to broadcast a 0 in there. Look at this beautiful art. I might actually save that one. That one's an art piece. And if we render this, hopefully nothing has changed. We still have all of our jagged edges. We don't have our abstract art anymore. So how do we fix this? Well, right now, what we're doing is we're just sampling the center of our pixel a bunch of times. We want to be sampling at all these random points instead of at the center a bunch. So what we're going to do is we're going to create an offset. So vec3 offset, and we're going to make a quick little function here to help us make this offset. We're going to go vec3 random in square, and we're going to return random in range -0.5 to 0.5, and random in range -0.5 to 0.5, and 0. And if my now add this offset, which is the random in square, to our pixel location, when we run this offset, I don't want to add the offset at the end. I want to go on to x and add the offset.x. I want to go on to y and add the offset.y. And that way, I'm not going way too far out. I'm not manipulating it in screen space instead of in world space, because going one out in world space gives us a blurry mess. Isn't that fun? If we now run this one, you notice that our edges now have this nice blurring to them. You notice we can see the random artifacts. So if we take more samples, it'll get better. But as a general rule of the edge is fuzzy now. There are some particular sampling algorithms. Like, I believe the one that everyone uses takes a point here, 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 and here. So kind of at quarter positions, like a rotated diamond type thing. But we're just doing random. So we have multisampling now. That's starting to take enough time that it's probably worth our effort to indicate where in the process of rendering we are. So at the end of each iteration of the big loop, so each row of our image, we're going to see out our y, and we're going to std inline it. And now when we run that, we should get a little printout telling us how far into the image we are. And it's kind of long. It takes up a lot of space. So I'm going to show a little trick here. If instead of doing an end line, we flush, before we print out y, we can print out a string, which is 10 backslash characters. And just like a backslash, when you're writing, like in a text editor gets rid of a character, a backslash in the terminal will get rid of a character. We'll put an end line at the end here. And so now what we're going to do is we're going to print out a number, backslash it away, print out a number, backslash it away. And so what it'll look like is we just have one number counting up. Look at that one number counting up. Isn't it cute? Okay. So now let's do a nicer sample. So we'll up our sample count to like 64, and it'll take a little bit. We can watch it go up slower. And now when we look at the result, there should be none of the randomness artifacts. It should just be nice and smooth. The more samples we get, the fewer of those randomness artifacts we're going to get. We're going to make a scene. So instead of just having one sphere that we hit, we're going to have 2 or 3. So how do we do that? Well, inside here, we're going to go std optional hit info, and we're going to create a hit scene function that just takes our array. And then in here, instead of hitting the sphere, we're going to grab that and put it in here real fast. We're going to hit our scene with our array. So what we can do, our simple approximation of how we blend multiple objects together is we just call it multiple times. So if auto hit equals hit sphere hit, then we return hit. And otherwise, we can do another sphere, a bigger one. This one is going to be kind of a ground plane. And so we're going to put it at -50, and we're going to make its radius 49.5. It's going to be a really big sphere down a ways. And since it's so big, it's going to look like it's almost flat. And then if we fail, we just return nothing. And we should see that there are a couple of weird artifacts happening. So what we need to do is we need to cap the distance. So in our hit sphere function, we're going to take in interval ray bounds. We're going to start that at 0. And we're going to define a new interval struct. So struct interval float min equals negative stud numeric limits float infinity, and float max is going to be positive infinity. And we're going to have a little helper function that'll be useful for us here. We want to be able to check if the interval contains a point. So bool contains a float t, make that const, and we're going to return min is less than or equal to t, and t is less than or equal to max. But we don't actually want contains. We don't necessarily want the bounding points included, especially if we're checking infinity all the time. So we're going to have bool surrounds float t const, which is going to be almost the same computation, but we can't include the endpoints. If the interval contains something, right, the endpoints are also included. If it just surrounds it, the endpoints aren't included. And so now we're going to do a little bit of testing on our root now. Remember, I said we were going to come back and ask what if the other root was needed. And it'll be needed if the ray bounds dot surrounds root. So if the bounds that we're considering does not include the root, we need to try the other root. So root equals -b plus the square root over 2 times a. And if the ray bounds does not include that root, then we failed to hit. So what this does is this allows us to add like depth to our system. So if something is too far away, we won't hit it. And then in our scene, we want to start tracking the bounds. So to track things, I'm going to have a std optional hit info out set to empty to begin with. And I'm going to go interval current bounds is going to start at 0 and go to positive infinity. And we're now going to start passing the current bounds to each of these hit functions. And instead of returning the hit right away, what we're going to do is we're going to update our output hit, and we're going to update the current bounds dot max to where we hit the t. So now we're going to only consider something if it's closer than that hit. So this is something called depth calling. So we don't consider a hit if it's deeper into the scene than our current hit. So what that means is that if I have an object behind me and then an object in front, if I hit the behind object, I'll get a depth, right? And then if I hit the in front object, I'll overwrite the depth. But if I hit the front object, right, and then try to hit the back object, the front object will be closer, so I won't hit the back object. So we'll do the same thing, out equals hit, current bounds dot max equals the t that we hit, and we return out, which by default is an empty optional, so no value. And if we run this, we have our beautiful scene. And it's no longer sampled, so edges are funky. But if we were to bring up the big sphere, so it's at a radius of 50, that means it'll overlap, and we don't do this bounds checking, what's going to happen is that since the old sphere is hit first, it'll look correct. But if I swap the order, we don't have the depth checking, so the objects will be rendered in the order. Remember that the big sphere is supposed to be halfway overlapping the little sphere. So right now this is wrong. It's just rendered based on the order. But if we turn back on that maximum hit calling, now, no matter what order we render the two spheres, the behavior should be correct. Because things get really weird if we're drawing stuff and the order we draw things changes how it looks like, right? We don't want that. That's bad. So this idea of depth calling helps us to fix that issue. We're going to talk about something called the rendering equation. It's sometimes also called the light equation, and we're just going to write it down real fast. It says that the light outgoing at some point in some direction is equal to the light emitted at that point in that direction plus the average over hemisphere. I'm writing down a simplified version. In the normal rendering equation, you're going to get integral there, but the integral just says average over a hemisphere of the incoming light at that point in an incoming direction times the BRDF at that point, considering the incoming and outgoing directions, times the dot product of the incoming direction with the normal of the surface. Okay, so what the hell does that all mean? Well, this term, right, says that if the surface is a light source, any light that we're generating is part of the output. That part makes sense, right? If we are emitting light, the output light will be the light that we emitted. So then this average over a hemisphere stuff basically says, okay, I have this surface point. I want to take the hemisphere, so the half sphere, centered at that point, and I'm going to sample the light in every single direction. So omega I is going to be every single direction inside that hemisphere, every possible direction. It turns out that computers are not good at solving for every possible direction. So there's an unfortunate property of this equation. This average over hemisphere part makes it unsolvable, which is just a mild concern, right? But that's not necessarily a deal breaker. All that means is that we need to do approximations. So what are we actually computing as we do it for every direction inside of this hemisphere? Well, we're taking the light that's coming in and we're multiplying it by a bidirectional reflectance distribution function. Multiplying by the dot product of the incoming direction and the normal basically tells us how aligned the light is with the normal. And so we can get brighter areas where the light is straight on and darker areas where the light is closer to zero. We're going to start off by implementing what's called diffuse lighting. So diffuse lighting does a couple of interesting simplifications to this process. So in diffuse lighting, our BRDF, so our material, is a constant color called the albedo. So albedo is an interesting measurement that most people aren't used to thinking about. Albedo is how much light gets reflected. So let's think about that definition for a second. How do you see things? Well, light gets shot by the sun, and then it bounces around a bunch of things, reflecting, and eventually it reflects into your eyes. So color is what gets reflected into your eyes. So what this means is that if a surface reflects a lot of red light, but not a lot of other light, it will look like it's red. So this is basically a mask as to what the incoming colors look like, and then they get filtered through this mask to find the outgoing color. So to compute this, we're going to need to add a little bit more information to our hit record. So the first thing that we're going to add to the hit info is a color F called the albedo. So now what we can do is in our scene here, we can go out albedo equals, say, 100 for a red albedo, although we're just going to set it to like a half gray, so 0.5 gray. And then we're going to set the ground to a slightly darker gray, so an albedo of like 0.3, so a slightly darker gray. So in this, we take the camera and we shoot the rays from the camera. So we do the opposite. Taking rays from light sources means that not a lot of rays are going to hit the camera, so why do we care about any of those rays? Instead, we're going to shoot rays from the camera, and since we're shooting rays from the camera, we're guaranteed that those rays are going to be useful in some way. So, just like we implemented last time, we calculated a big old plane in front of the camera, and we generated rays that go through that plane. We added albedo, and in our scene, we've set up the albedo. So now, how do we calculate something useful with the albedo? So, instead of returning the normal color here, what we're going to do is we're going to calculate what's called a Lambertian reflection value. So the idea with Lambertian diffuse, or diffuse in general, is that when light hits a diffuse surface, what the light is going to do, let's draw a red light. So our incoming light is basically going to go any way it wants. It's just going to randomly bounce off. The only constraint here is that random bounce has to be inside the hemisphere. So like it can't bounce like into the surface. In fact, that's called something different. That's not a reflection anymore. That's a refraction because the words have to be similar. So we're going to implement this behavior where we get a random bounce. What you're going to see is that this looks a lot like the average material. It's like a not shiny kind of matte material. So let's implement it. What we're going to do is we're going to create a vec3. So the other interesting thing here, right? Since the BRDF is constant, that means that bouncing is random. So we need a vec3 random in hemisphere, and we need a vec3 for the normal. So we're going to make a vec3 random unit vector. And so we're just going to return random in range 0, 1, random in range, random in range. And since I said it's a unit vector, we're going to normalize it. So U is equal to a random unit vector, x3. And if the dot product of U and the normal is less than 0, so if they're not facing in the same direction, what we're going to do is we're just going to negate U. So U equals negative U. If the vector is pointing into the surface, we're just going to point it out the other way. So now that we have our random in hemisphere, what we're going to do is we're going to go that our vec3 diffuse direction is going to be random in hemisphere with our hit normal. And then we're going to have our incoming light. So this is our omega I is going to be equal to just shooting another ray. So ray color, and our ray is going to be our hit position, and our direction is going to be the diffuse direction. So we're going to shoot another ray from wherever we hit in the random direction in the hemisphere we just decided. And whatever color we find in that direction is going to be our incoming light. So now what we're going to do is we're going to return our hit albedo times our incoming light. So we're multiplying our BRDF by our incoming light. And if you remember the inside of the rendering equation, right? So the part inside of for everything in the hemisphere was incoming light. So light at the point from W incoming times the BRDF at the point times omega incoming, omega outgoing times omega incoming dotted with the normal. But you notice that this part has kind of magically disappeared from what we're returning. I'm not returning this multiplication by the normal. We're going to stick a pin in that idea, and we're going to see how this looks. Okay, you ready? So we've traced, and ideally, we now have the world's most grainy little ray trace, but we can clearly see that this sphere has some shadowing, right? If we give the tracer a couple more samples, we should get a slightly better result. And this is starting to look like an actual scene that you might render. It's super grainy, There's a lot of detail missing, right? But we can like see the contact shadow between the two spheres. They're not just gray. They're starting to pick up some of the bluish tint from the sky. This looks like something that you might see outside in a very simple world. So we're now going to come back to this question of why are we not multiplying by the normal? Why does it look fine despite the fact that we're not multiplying by the normal? Like, as you can see, where the light is hitting like on the edges, the more grazing angles are starting to get subtly darker. Why is that? Well, the ray tracer sneaks in this multiplication by the normal in the fact that our random unit direction is going in the hemisphere. So the way that diffuse rendering works, that in a ray tracer in particular, that dot product gets baked in. So for some reason that I honestly do not fully understand the math behind, we can ignore the dot product when working with ray tracers. But what I'm going to do now is I'm going to tweak this diffuse lighting and to make it a little bit better. So this isn't going to be a diffuse direction anymore. This is going to be a Lambertian direction. So Mr. Lambert decided that he would create a new tweak to the diffuse algorithm that makes it better. People visually like Lambertian diffuse better than normal diffuse. It models the real world a little bit better in our brains. It's also slightly easier to calculate. The way we calculate it is that we take a random unit vector and we add that random unit vector to the normal. So what we're doing is instead of that previous picture where from the point we were going out in every random direction along the hemisphere, what we're now going to do is we know the normal of the point, right? So we're going to drop a new point there, and we're going to sample everything in the sphere centered on that new point that's 1 unit off of the surface in the normal direction. So we're going to start shooting our random directions off of that point. What this buys us is that the directions are going to be biased more towards being in the normal direction. Basically, if the random direction happens to be on the positive side, we're going to be biasing towards the normal. We're just going to be shooting a ray towards the normal. And if we give that a quick render, we should see that it looks more visually appealing. So let's pull up a side-by-side of diffuse and Lambertian diffuse. You see that the shadows become a little bit more pronounced, and you see a little bit more of the bluish lighting on top of the sphere. This one, the coloring is a little bit more homogeneous, whereas this one, you get bands of like lighter color on the top and darker color at the bottom. So now I mentioned that albedo affects how much light gets reflected. So what happens if instead of reflecting light uniformly, we like only decide to reflect the red color? What do you think is going to happen to our surface now? So if we only reflect the red light, you notice that our sphere now has a red tint because we're not reflecting any of the blue light or the green light that hits us. So all the light that actually appears to us, everything that makes it to our camera eye, is going to be red. Also, you can kind of tell it's hard to see with the graininess. So let's do a really long render. Let's do like 1024 samples. It's going to take a second. But you can kind of sort of almost see that we're getting a subtle amount of red reflected around the red sphere on the big gray sphere. What happens if instead of having a diffuse material, we want to have a metal? How do metals work differently than diffuse materials? Well, in a metal, we don't have this random behavior much anymore. We're gonna put an asterisk on that much. Instead, what happens is we have our surface and we have our normal, right? And then our incoming light is going to just reflect around the surface normal. So if you recall, we have the reflect function, right? Which is v minus 2 dot v with n times n. So we take our vector, we subtract off 2 times the dot product of v with the normal vector and multiply by the normal vector. And that should give us the reflection along the normal vector. If you don't believe me, go check the math video from earlier. There's a whole video on the channel where we prove, as part of what happens, that is the correct formula for reflection. The other thing, though, is we might add a little bit of randomness. So what we're going to do is we're going to add a fuzz/roughness value. And what this does is we're going to have, say that this is a 0.1 sized roughness. We're going to make a little sphere of size 0.1. So R equals 0.1. And we're going to randomly add on a vector in there. So when fuzz is 0, we're going to have perfect metal reflections. But when fuzz goes to 1, right, we almost wind up with like a diffuse type reflection. And that just determines how perfect the reflections are. Fuzz really close to 0 creates something that looks like a mirror, whereas fuzz really close to 1 creates like a really grimy surface that's almost diffuse. So the way we do that, we have vec3 metal direction equals the reflection. So StinMath reflects of the incoming, which is, where did we put the camera? Camera center is at 0, 0, 0. So 0.3 camera equals 0, 0, 0, which means that vec3 incoming is equal to hit point minus camera, hit pause minus camera. But we can simplify, since we know that the camera happens to be at 0 right now, just to the hit position. So we're going to reflect our incoming direction along the hit normal, but we are going to make sure that we normalize this value. So the last thing that we're going to talk about is we're going to go into the hit info, and we're going to add a bool is metal, and we're going to add a float fuzz. So now what we can do is in our scene, and we're going to set this to false and this to 0, is in our scene, we can go out is metal equals true, and then out fuzz equals something like 0.1. And now we have our Lambert direction and our metal direction, and we can go vec3 direction equals hit is metal, and we can use the metal direction. Otherwise, we can use the Lambertian direction, and then we can use direction. So we now have two very simple BRDFs. Both of them basically apply a constant, right? With this one, the constant that we're applying is just the color. And with this one, what we're basically saying is for every direction that's not the reflection direction, it's 0. And in the reflection direction, it's constant. So if we formalize that a little bit, the BRDF or diffuse is just albedo. So what that says is for every direction in the sphere, we just multiply it by albedo. Okay? It's just a constant. And since the probability is just this one value, we can sample any probability randomly. We mentioned that the rendering equation is unsolvable. We can only approximate it. And the way that a ray tracer approximates it is by samples. So since every ray that we shoot can take a random path, we're going to wind up getting a couple of different samples of the BRDF. And so the more samples you take, the better an approximation of the rendering equation you get, but also the longer it takes. And then our BRDF metal is a piecewise defined function where the reflection is albedo if the incoming light direction is the reflect across the normal of the outgoing light direction and 0 otherwise. So our probability is 0 that there's any light if it's not the reflection and the albedo otherwise. And these two BRDFs give us already pretty okay looking surfaces. The problem is that we are running out of stack space because we should have a size t depth equals 0 here. And then if the depth is bigger than like 64, then we're just going to return black. And every time we call ray color, we're going to give it depth plus 1. We are stack overflowing. That's the problem we're hitting. It's not a math problem. It's a me problem. It's an implementation problem. Let's go 256 and let's up the switch to release. Give it a run. Let's hope that we get something nice. The more samples we give this, right, the better of an approximation of the actual rendering equation this becomes, and the less all of these artifacts go away.